Well, the short story on the stress tensor should have given us a good general sense of how stresses vary inside a body in a qualitative way. That is, that you have a variety of different forces acting on any external boundary in some little chunk of matter in the ground. But when you look inside that chunk of matter, the way those forces combine depends upon the orientation of the plane inside the body that you're looking at, in addition to the forces themselves that are acting on that chunk of ground. So, evaluating those expressions, I've mentioned in class, actually evaluating those expressions is very easy today with calculators and computers. Before we had those tools and we were reliant upon basically long arithmetic to do any calculations, long arithmetic and trigonometric tables, a much more efficient way of solving certain complex problems was to find a comparable graphical solution where you could arrive at the information you needed by making measurements on a drawing that represented the solution in some fashion. And that's exactly what the Mohr circle is. We don't need the Mohr circle today for really anything more than a pedagogical device to help to visualize stresses. And they are very good for that. So I'm going to take you through the way in which the Mohr circle is constructed in a very simple setting. This is going to be in 2 dimensions only. Mohr circles can be applied to 3 dimensions, and we're only going to look at some of the very first results. But this will be another exercise that will help you to visualize what's actually happening in the ground. So once again, our object is to find out what the internal stresses are acting on some little parcel of ground, dV, or as we've been working in 2 dimensions, dA. There may be any combination of forces acting on this: normal forces, shear forces, etc. These are all known to us, and what we discover through the Mohr circle calculation is how all of these external forces are expressed inside the body once we have decided the orientation that we are looking at. And the reason that we have to choose is it's only once we decide upon an orientation that we can pull out a single vector that describes the forces acting on that plane. So, to do this, we're going to go back and do a force balance exercise on our little triangles we've done before. I'm going to do it a little bit differently this time because of the way that the arithmetic is going to work out. You remember last time we calculated how the x and y components in this local coordinate system varied depending upon the angle, theta, of this cut and the applied stresses, sigma xx and sigma yy. Well, this time we're going to do the same thing, except that instead of looking at the x and y components of the reaction stress, I'm going to look at the components acting in the normal and shear direction on that cut surface at some angle theta. And I'm going to call these sigma prime and tau prime. So we're going to try to solve for those. And to do that, instead of balancing forces along the xy coordinate directions, I'm going to balance them along a set of axes that are aligned with the normal and shear stresses acting on that cut surface. In other words, this x prime, y prime axis is rotated by the angle theta from the xy axis. So, as we have before, we have to convert these stresses to forces by multiplying them by the area of the surfaces on which they act. And this time I'm going to call this diagonal surface DL, the D to remind us that this is a small surface. And then the left-hand vertical surface will be DL cosine theta, just by the trigonometry of the triangle. And down here at the bottom will be DL sine theta. So those are the areas or lengths in the two-dimensional case that we'll be multiplying our forces by. Now the other thing we have to do is break down our sigma xx and sigma yy into force components that are parallel to the x prime and y prime axes. So let's draw in those components. I've drawn my sigma xx and sigma yy here a little bit longer so that we can see this more easily. The sigma xx on the left will break down into a component oriented like that, and another perpendicular component oriented like that, where this is the angle theta. So you can see as the theta up here opens up, the axis swings down in a counterclockwise direction from sigma xx, and we have one component parallel to sigma prime over on the right-hand side, and another component parallel to tau prime. Same thing on the bottom, where we have a tau prime component over here, and a sigma prime, that is tau prime parallel component, and a component parallel to sigma prime over here, where this is the angle theta. And now let's just write down what those values are based on the trigonometry of these little triangles. And those will be, this one here is sigma xx cosine theta, and this one here is sigma xx sine theta. And down here, this component is sigma yy cosine theta, and this one is sigma yy sine theta. So now we have 1, 2, 3, 4 forces acting in the x prime or y prime directions to which sigma prime and tau prime on the angled surface have to react. So let's write down the sum of forces for each direction here. I'm going to start by summing forces in the x prime direction, and that acts in that sense. And those are sigma xx cosine theta, that's the magnitude of the stress, times dl cosine theta, that's the size of the left-hand side of the triangle, making that a force. And then I will add to that sigma yy sine theta, that's the component of sigma yy at the bottom acting in the x prime direction, and it's multiplied times its area, which is dl sine theta. And then finally, in opposition to those, I have sigma prime acting on the surface dl, and those all need to sum to 0. Then summing forces in the y prime direction, and that's positive in that direction, we have a minus sigma xx sine theta times its area, dl cosine theta. And that's a minus because it is acting in the negative sense of the y prime axis. And then acting in the positive sense of the y prime axis, we have sigma yy cosine theta acting on its surface, dl sine theta. And opposing that is tau prime times its area, dl. And again, those will sum to 0. Now, we can see from these that the dl cancels out of each term, as it should. And all we have to do is gather some terms here, and we can write down sigma prime as a function of the sigma xx and sigma yy, and that is sigma xx cosine squared theta plus sigma yy sine squared theta. That's a nice symmetrical result. And tau prime works out to be minus sigma xx sine theta cosine theta plus sigma yy sine theta cosine theta. And we can rearrange this tau prime term one step further, and it looks like this: sigma yy minus sigma xx times sine theta cosine theta. So there are my expressions for the sigma prime and tau prime, the normal stress and the shear stress acting on the surface cut at an angle theta in response to the far field or applied stresses sigma xx and sigma yy. I can go one step further using a couple of trigonometric identities, and I'm not going to take the time to go through that right now. I'll just tell you that this is simply algebra along with some trig identities that will allow us to rewrite these expressions in a form which is going to lead us to the graphical solution of the Mohr circle. And after that rearrangement and a little bit of algebra and trigonometry, we have sigma prime is equal to 1/2 sigma xx times 1 plus cosine 2 theta plus 1/2 sigma yy 1 minus cosine 2 theta. And we can rearrange that to this: sigma xx plus sigma yy divided by 2, and you'll notice that that's the mean stress applied to the body for the outside forces, plus sigma xx minus sigma yy divided by 2, and that times the cosine of 2 theta. And then tau prime can be rewritten as sigma xx minus sigma yy divided by 2, all times the sine of 2 theta. So now we have sigma prime and tau prime written in a more compact fashion in terms of the applied stresses, sigma xx and sigma yy, and the angle theta expressed in this simplified form of just the cosine 2 theta appearing in the sigma prime term and the sine 2 theta appearing in the tau prime term. Notice also that the first term of the sigma prime is the mean stress. The second term is half of the difference between the two stresses, and that same thing applies to the shear stress here. So now let's take these over and make a plot of sigma prime and tau prime as a function of the angle 2 theta and our applied stresses sigma xx and sigma yy. Here are our Mohr axes with the normal stress sigma on the horizontal axis and the shear stress tau on the vertical axis. And we are going to plot these as a function of theta. Actually, not a function, but a parameter. In this case, we're treating the sigma and tau both as dependent variables and theta as the independent variable. So this is really a parametric relationship. It's a little bit different from a normal f of x type graph where you plot the independent variable x on the horizontal axis and the dependent variable f on the vertical axis. In this case, both sigma and tau are results of the calculation, and the independent variable, which we'll be able to measure on the plot, doesn't actually appear as one of the coordinate axes. Before we start drawing, though, take a close look at these expressions for sigma and tau. Let's think just a little bit about how they interact. And I'm going to just start at an arbitrary point. Actually, not an arbitrary point. Let's start at the mean of the normal stresses, sigma xx plus sigma yy. And we'll just put a point right there, and we'll let tau be equal to 0 for the moment. We'll ignore it. And notice that that term is a constant, and then the second term here oscillates around the mean with a magnitude of sigma xx minus sigma yy divided by 2. So that's half of the distance between them. And it will make one complete cycle when 2 theta goes through 360 degrees. So that means that sigma is doing something like this. It's going from the mean stress out to the maximum stress, back to the minimum stress, and then returns to the middle. And it just cycles back and forth like that as 2 theta goes through 360 degrees. At the same time, the shear stress is also oscillating, going through a full cycle as 2 theta goes through 360 degrees, and its magnitude is going back and forth between a positive sigma xx minus sigma yy divided by 2 and a negative value of the same. So it's going like this. And you notice that that range of the oscillation of tau is the same as this range of the oscillation of sigma prime. So when sigma prime and tau prime act together, they'll describe a circle on this space. Let's just quickly sketch out what that would look like. Starting with theta equals 0, the expression for sigma prime would be at its maximum value, because the second term, when cosine 2 theta is equal to, when 2 theta is equal to 0, cosine 2 theta will be 1, and so sigma prime will take on its maximum value. And let's just say that that's right here. Then tau prime, we can see that that's going to be equal to 0, because sine of 2 theta when theta equals 0 is 0. So our starting point is right on the sigma axis, and as theta increases, the cosine of 2 theta diminishes from its maximum value, and the sine of 2 theta increases. And that describes a circle that follows a path like this. And when we get to 2 theta equals 180 degrees, we have come all the way around a half a circle, and we're over here. And the sine has gone through its peak and back down to its trough, and the cosine has gone through its trough and come back to its peak, although it's now in a negative sense, where the second term is being subtracted. And then if we go through another 180 degrees, we come right back around and we complete the circle. So when 2 theta goes through 360 degrees, both of these values describe a circular path straddling the sigma axis and form a complete circle. Well, let's stop fooling around scribbling and actually plot something on the Mohr circle axes. I've chosen for my horizontal and vertical stresses sigma xx equals 2 and sigma yy equals 6. That will give us a mean stress, and that's the first term here in the sigma prime expression, of 4, the midpoint between 2 and 6, and the radius of the circle, that's the second term, is going to be 2, half of the distance between sigma xx and sigma yy. If we start at theta equals 0, then the cosine will be 1, and sigma prime will take on the value of sigma xx. You can see the first term we'll have 1/2 sigma xx plus sigma yy, and the second term will subtract off that sigma yy and leave us with a whole sigma xx. Also, at theta equals 0, tau will plot as 0. So we can place that on the plot as our first point, and I'm going to put it right here at sigma equals 2, tau equals 0. And that is for theta equals 0, and 2 theta also equals 0. Now let's think about what orientation that means. Remember that when we drew our free body diagram, the triangular section, and calculated these forces, our theta was this angle here between the vertical left-hand side and the hypotenuse of the triangle. So that corresponds to a counterclockwise rotation from vertical. So at theta equals 0, we are looking at forces acting on a vertical plane. And that, of course, would be sigma xx. So that makes sense. When we're in the theta equals 0 position, we are looking at this vertical slice orientation, and the force which is acting on it is sigma xx, and so the reaction force on the other side would also be sigma xx. Now, let's start moving by intervals around the circle. Now, which way are we going to move? Well, as I said, theta is counted counterclockwise from the vertical, so when we leave the first point at theta equals 0, we are going to move in a counterclockwise direction in the ground and also on the circle. And we are rotating about a point, which is the middle of the circle, at sigma equals 4 and tau equals 0. And as we move along through theta, theta in the ground, 2 theta on the Mohr circle, we will calculate values of sigma prime and tau prime for that orientation, and each of those dots will plot in this sigma tau space. So let's tabulate a few of these and see where they plot on the graph. So we've already plotted our point at theta equals 0 and sigma equals 2. Let's now move 20 degrees in the ground, which corresponds to 40 degrees on the Mohr circle. And using the equations, we find that sigma equals 2.47 and tau equals minus 1.29. And those will plot on the Mohr circle right about here. Going further, if we go to 45 degrees in the ground, that's 90 degrees on the Mohr circle. So we're going to be at the bottom of the circle, where sigma equals 4, the midpoint, and tau equals minus 2, which is as negative as it gets, at the bottom of the circle. And that one will plot right about there. And then continuing around the circle, if we go to, say, 60 degrees in the ground, that's 120 degrees on the Mohr circle, and the calculated values for that are 5 and minus 1.73. And that plots about here. Then finally, when we get to 90 degrees, that's 180. And we are at the far side of the circle. And then, of course, we are at sigma equals 6, and tau is back to 0. And we are right there. So there's the first half of our circle. And when we complete this, we find that, indeed, we get a full circle. Like so. A couple of things we can see here. There are 2 orientations in the ground. One here, where we've already plotted, that's at theta equals 0, which is a vertical slice where only the horizontal forces act, where there is no shear stress acting, only normal stress. And there's another one over here on the other side, separated by 180 degrees on the Mohr circle, or 90 degrees in the ground, so that is on a plane which is horizontal, acted only by vertical forces. where there is also no shear stress. Those are called the principal stresses. They are always the largest and smallest of the normal stresses, and those positions are always occupied by zero shear stress as well. And that's just a characteristic of the circle. When it has its maximum value in the sigma direction, it's crossing the tau equals 0 axis. At 90 degrees on the Mohr circle, or 45 degrees in the ground, the shear stress reaches its maximum value. So that means that there are two orientations in the body, one like that and another like this, along which the shear stresses are at a maximum value. Now, there's an important point to make here. What we've been doing so far, I've been actually calculating the values of the normal stress and shear stress for various different orientations in the ground, and then plotting those on the Mohr circle. This is by way of demonstrating to you that the normal and shear stress vary in this organized pattern. Now, we don't have the Mohr circle so that we can take values that we already know and demonstrate that we can draw a circle using them. It actually was used the other way around. If we don't have the capacity to do the calculations to get these numbers, we can use the Mohr circle construction to find out what those intermediate values are. So let's do a couple of examples that will show you how you actually use the Mohr circle to find the stresses. So here's a specific example. We're given the values shown here. We know from some other source that the vertical normal stress sigma yy is 5.8, the horizontal normal stress sigma xx is 2.8, and also acting on the horizontal and vertical planes are shear stresses of tau xy is -2 and tau yx is +2. Again, those are equal and opposite so that they're balanced in moments. Let's take those sigma tau pairs and plot them on the circle. You can see I've done that here. The first one, A, 2.8 and -2, plots down on the lower left, and B, 5.8 and +2, plots on the upper right. So those are the two orientations for which we know the state of stress from some other means. And what we want to use the Mohr circle for is to draw a circle which allows us to evaluate the stresses in any other orientation in the body at this point. So to do that, since we know that the circle has to straddle the sigma axis, we can draw a line that will join A and B and will form a diameter that will cross the sigma axis at the mean stress, the midpoint between sigma xx and sigma yy, which also forms the center of the circle that we will draw from these data. So let's see if we can draw this in. Here is the line joining our points A and B, crossing the sigma axis at 4.5. It's a little bit difficult to do this very precisely on an iPad. For one thing, I can't draw a proper compass circle easily because I can't pin the center on this hard plastic surface without damaging it anyway. So I'm going to try to draw this as best I can here. And it's going to go around like so, and I don't quite hit A properly. You get the idea. If you're doing this in practice, you do it on a much larger scale and much more carefully with graph paper and a proper compass, and you can get quite precise results doing that. So there's our Mohr circle, and here are our values A and B that we were given, but now we can turn in any other orientation and find what acts on that plane. So let's start by looking at point B here, which is the set of normal and shear force acting in the vertical direction on a horizontal plane. So I'm going to draw that plane in over here on our XY diagram, and that is the surface or the orientation that B applies to. So let's find out where the principal stresses are. First of all, that is the orientation at which those shear stresses disappear. This is different from what we've done so far in that the values that we're given have shear stress components to them. Because the Mohr circle always crosses the sigma axis, there are always 2 points where the shear stress disappears, and those are here at the far left and far right of the circle, where they cross at approximately sigma equals 2 and sigma equals 7. And to find out where that is in the ground, I need to get my protractor out and measure this angle here. And when I do that, this appears to be 50 degrees. So that is 2 theta. And so now we can carry this over here to our XY space and plot a single theta, which will be 25 degrees, and it's turning in the clockwise direction from B. So what I need to do here on the right-hand side is construct a plane that is rotated by 25 degrees clockwise from the horizontal plane labeled B. And that looks about like this. All right, so this is the orientation of the principal stress sigma equals 7. So I'm going to call that sigma max. And on the other side, the left-hand side here, we have a value of 2, which is on a plane which is rotated by 50 degrees in the Mohr circle space clockwise from the orientation A, which is a vertical plane. Let's grab a different color to do that. So here is the vertical plane that the stress sigma xx equals 2.8 acts on. And if we rotate clockwise 25 degrees in the ground from that plane, we have the orientation that the minimum principal stress, sigma xx equals 2.8, acts on. And of course, that is also perpendicular to the 25-degree plane that we calculated already. So that's the orientation that sigma min appears on. We can also calculate where the maximum shear stress appears. On the Mohr circle, that maximum shear stress is here and here, and to that point we would have to rotate counterclockwise by, well, it would be the complement of 50 degrees, so that would be 40 to make up 90 degrees. So if we rotate counterclockwise by 40 degrees from either the A or B orientation, we will find the planes of maximum shear stress. So let's draw those in. Rotating 40 degrees in the Mohr space from B to the maximum shear stress corresponds to rotating 20 degrees in the counterclockwise from B in the XY space, and that puts us in a plane that looks like that. So that is going to be one of the planes of maximum shear stress. And it's positive in this direction, so I anticipate it's going to act like that. And then the other maximum shear stress down here at the bottom is offset by 180 degrees in the Mohr circle or 90 degrees in the ground. And so the other shear stress, the other maximum shear stress that we expect to find is going to be on a plane that looks like this, perpendicular to the other maximum shear stress. And that one is going to act in a negative sense, like this. So these are examples of how you can take one set of normal and shear stress acting at some orientation in the body and calculate the shear and normal stresses at any other point in the body. Now, why would you want to do this? Well, there's lots of obvious reasons. One of the main ones is that you may have a material which is subject to failure under either shear or normal forces. And you notice that the values that we were given originally here, A and B, are neither the greatest normal stresses or the greatest shear stresses that appear in this body. We know these stresses, but these stresses here might be beyond the strength limits of this material. And it's just buried in some orientation in the body, and by this means we know how to find that. So there's one example. I'm going to wrap this up now, and I will post a couple of other examples in a following video. But I think this gives you the idea of how this works. And again, just very quickly in summary, if we have the orientation of the stresses somewhere in the ground, and I'm going to draw my little box at an angle this time because it doesn't have to be horizontal or vertical. It can be anything. And we are given the state of stress in some orientation, and we can then rotate to look at a different orientation. I'm going to just rotate this box in some other orientation, and we can find out what the stresses acting on that plane are. And once again, the notion of the stress as a tensor concept, we can find the stresses at a position in space, a position in time, and also we have to find an orientation in the body, because what we're trying to get at here is a stress vector. In other words, a combination of normal and shear stress acting on some orientation. And you can't do that for every orientation in the body without using the tensor representation of the stress. And then, as we described before, when you apply the tensor calculation to this using the outer normal of the plane that you're interested in, and that is to take, let's say, these are the direction cosines of the orientation that we're interested in, that will give us the stress vector acting on that orientation. And once again, the stress vector is the vector combination of the normal and shear stress acting on the body.